Good afternoon, everyone. Welcome to another episode of How to Run Keras and Tensorflow in Rstudio. Specifically, today we'll talk about RNN. So today is going to be a long video. It's going to be a lot of different situations that you might actually encounter during a model development on this topic. So I have arranged seven different subtopic on this RNN and try to walk you through one by one. So if I'm able to do it fast, I'm trying to walk you through all seven in a single video. If not, you'll see multiple videos and you know where to find the next one. They're all in the description below, or I'll organize a playlist and so on. So the first thing, of course, is understand the data set that we're dealing with. Why do we use RNN instead of other normal neural network or other type of neural network? So RNN, recurrent neural network, what it is, when do we use it, and why do we use it? So let's refer to a Wikipedia article over here. So RNN is actually whoa, that's a huge zoom. So recurrent neural network. So what does a recurrent neural network differ from a normal neural network is that the neurons is able to remember the previous state. So that makes it extremely useful for, let's say, time series data. For example, today I'm actually going to use weather data, which is why we are using it. We're using our this RNN for the data prediction. So of course, it's also very famous for using, let's say, speech recognition, handwriting recognition, where one state is dependent on the previous state. So if you are running good, the next likely is going to be morning. So you can actually predict the current data based on the previous data, where that is a high significance to what they're going to be based on what they are previously. So if you have a bowl of, it's going to unlikely to be beef, but it's going to be soup. So the probability is going to change based on that. So RNN is a lot more useful when you have data that are in series, that one is relation to another. While in normal neural network, they're independent. So if in 10 variables in a normal feed-forward neural network, they're independent of each other, there should not be, they're not calculated based on each other. If that makes sense or not. So in time series, you want that progression to influence, and you want that progression to make your predictions. Okay, so there are two main things, there are two main model networks, there are two main networks and units that are used in RNN. So the first one is long short-term memory. So it's a lot more established, it's a lot more commonly used in a lot of things, on handwriting, speech recognition, stock market predictions, and data that are actually in series and so on. So there also is something rather new. It's called gate recurrent unit, GRU. So it's only described in 2014 by this person, Koo-Hyun Cho. It's performed slightly faster on smaller dataset, but it's a lot less strict than LSTM. It has a lot less parameters. It's faster to train, but in certain way it is not as better. It doesn't perform as well for certain dataset. So when do you choose which one? It depends on the data that you have, the situation that you have, and of course, how do you design your model and so on. And of course, again, what is your optimizer, what is your activation unit, and a lot of different parameters. And it's good to try both and see what happens and so on. Okay, so let's go to our R code over here. So today I'm using an R Markdown instead of a normal R script last time. An R script is much better in convey, let's say, efficiency, where you just want the code to work. It should work as a script where it should just execute without any problem, while R Markdown has a lot more space for you to write comments and code are a lot clearer to read. You are able to integrate many different type of code within a Markdown instead of just R. So if you go to insert, you are able to put all this bash, Python, RCPP, SQL, and Stan. So you are able to include all this chunk. And instead of running line by line like we did in our script last few videos, you are able to run the whole chunk. So it's a lot easier to run, it's a lot more clearer to convey a message, which is why I'm using it here. And secondly, my coding is also not optimized to run, it's optimized for the flow of the video. So don't show it to your boss and say that you're a very clean programmer. This is certainly not the best practice in programming. It's good enough, but it can be a lot better, and it will be a lot better in the different situation that you are in. Okay, so the data set is actually from here. It's from Amazon AWS, where it has a Keras dataset for a Jena climate from 2016 to 2009 to 2016 as a CSV. So this is the weather data in 14 different parameters. So I already download the data. It's about a few hundred megabytes. So I'm not going to download it here. I am just going to run to import the library. So there are only very little library that you need over here, and they're mostly just Tensorflow and R. So what this two code is that it set the directory, create a directory, create a folder in your downloads directory, and then it downloads the file into there, and then it unzip the file. Okay, so once you've done that, the read CSV will actually read that CSV which is rested in your download folder into an object called raw data. So if you run this chunk, you'll be able to load the data into your raw data and have a glimpse of it. So what the magic about glimpse that you're able to see all the different columns over here. So we have daytime, which is our time series indication. We have the pressure, the temperature, and all the different parameters from a weather station. Okay, so you're able to see there are 420,000 lines. It's a huge data set, and we're 15 variable. It's 15 variable including time date. So technically we have only 14 excluding the time variable that I described earlier. So the target over here we're trying to do is the temperature. So everything is supposed to be related to the temperature in some way, and we're trying to use all of this data to predict the temperature of, let's say, the next day, or in this case, the next 10 minutes. So the data is basically every 10 minutes, it will give a temperature, and we want to predict the next temperature on the next 10 minutes. Something like that, okay? So of course, the temperature fluctuates throughout the day. So from, let's say, this is 10 o'clock, sorry, so this is 12:30, and the temperature will steadily decrease until, let's say, 6 o'clock in the morning, and it will steadily increase until, let's say, 7 o'clock at night, and then it will decrease again, and so on. So we want to know how frequent is that, and how do we able to make a model so that we can predict what is going to happen in the next 10 minutes, and so on, based on all the data that we have. Okay, so the first thing is try to understand how does the data look like, what is the range that we're working with, what is the maximum, minimum, and so on. So we're using two ggplot functions over here to visualize. So this is the data across 420 different input. So you can see they're fairly consistent from -20 to +40 over here. So this is going to pose a problem to our neural network. It's not that nice to feed a neural network that is not within, let's say, 0 to 1, or -1 to 1, depends on your activation function. Because in ReLU, everything negative get cut to 0. ReLU don't process anything below 0 data, and most of the function will crush everything above 1 into 1. So you don't get really much thing outside of that range, and you can change the activation function by using a custom activation function. But today we're going to show you something simpler, which is actually to scale and normalize the data, or some people call it the standardization of data. So we are also not going to use the whole data set, because the training is going to be slow and development is going to be pretty slow. So if you actually look at over here, this is the first 100,000 line. They're pretty similar. So if I just cut roughly right here, you can actually get a whole curve in the first 50,000 line, and you are able to repeat this process over the other network without using so much time and memory on your training. So if you just cut the first 50,000, you should be fine. Or you can cut, let's say, 20 to 50,000, as long as you get the cycle. So since the cycle is about 50,000, we should be able to just get away with using the first 50,000 of the data, and so on. So this is how the first 1,000 data looks like. You can see that they're steadily increasing, and then say decreasing, and steadily increasing again. So it actually is a recurrent pattern. So it is very important for your network to be able to understand that this is a recurrent thing, so that they are able to better predict. So how long is the curve will be part of the thing they need to know, how steep is the curve in certain situation, and so on and so forth. Okay, so what do we do? It's going to be two things over here. For data pre-processing, we're going to, of course, convert the whole thing into a data matrix. That makes the calculation a little bit faster. And the first thing we're going to do is scale. So scaling actually change all the data to change the mean to the middle, and every data will be one standard deviation away. So that makes data from, let's say, 100 to 1,000, or let's say 1 to 10 to within the same scale, which is the point of scaling. And we again is going to apply a normalization function which change every data into 0 to 1. So everything lower will become 0, everything highest will become 1. We call this min max normalization. So we are writing a custom function on it and we're applying on it. And it's important that before you do the scaling and before you do the normalization, you record what is the minimum maximum and what is the mean and standard deviation. Otherwise, you would have a problem retrieving the data and try to actually predict the data later, because you only have the normalized and scaled data. You don't have the original data to work on. So if you keep the mean, standard deviation, minimum and maximum, you should be able to return the data back to its original state later. Okay, so this is the first 50,000 data. So we are doing a 60-40 split over here. First 60% is gonna be our training data, while the next 40% is gonna be our predicting data. Okay, so the column that we want to do is the second column, which is why there's a 2 here and 2 over here. So you look at the second. So we already removed the first raw data over here. So the second column actually refers to our temperature. So this is the temperature data. For prediction, this is our data input for prediction. Sorry, this is the data for training and this is the data for predicting. I don't know what I'm doing, it's a bit too hot in here. Okay, so the next one we're going to talk about generator function. So the problem is that when you want to feed a model feed or the model feed, you want to do a model feed in Keras, you have to feed the whole data set, the X and the Y, into the memory. And if you don't have a big memory in your computer, you're going to have a lot of problems. So a generator function is allowed to generate things on the fly. So instead of feeding the whole data set into the memory, at one time it tries to split that process up and only feed in a certain number of rows at a certain time. So instead of feeding in 30,000 of them right into the data set and see what happens, it's just going to be crazy. Feed generator will splice the data, or actually not splice, actually split the data up and feed in once at a time. So we're gonna actually do a custom idea later, and we'll just start with our first one. So just for a current recap, we have done what is the data set. So the data set is our sunspot data, the temperature data, while the RNN is used for a lot of time series data sets and so on. So we finished about a little bit on the generator function, but first let's go into the first non-RNN model. So this is a normal feed forward network, and let's see what's the meaning of flattened layer and how do we run an array into a non-feed forward network. So if you don't know how a feed forward neural network works, is that you have a bunch of neurons over here feed into another bunch of hidden layer, and this hidden layer feed maybe into another hidden layer, and then you get your output. So in this case, this is very straightforward. You feed in this, you get this out. Nothing really special about it. But the problem is, you can see here is a one-dimensional vector. This is not an array. So what you want to do when you want to feed in an array is something we call a flatten. So a flattened layer actually takes, let's say you have an array of 3 times 3. So this is the data you want to input. You run it through a flattened layer. So when you run a flattened layer, I can't write more than the character over here. I write through a flattened layer, this 3 times 3 matrix will become 9 neurons. So they just spread the neurons out, so that instead of a 2-dimensional array, 3, let's erase one of them. So 3, 3, 3. So instead of a 3 times 3 array, you get a 9 elements matrix. 9 elements. So instead of 3 times 3 matrix on the array, you get a 9 elements vector. So that is capable enough to directly feed into a neural network. But the problem is that you won't understand what is the meaning of this. So it kind of lost a little bit of idea from the original layout of the data, because there's a reason why it is an array and not a vector. But flatten it down, allow it to be directly fed into the network fairly easily without much modifications. so on. So here we're looking at a look back of 240. So what does look back means is that, how are we so fast over here? So is that every single step we're trying to use 240 steps behind it as a reference point, so that you are able to use 240 point to predict 1 point. 240, 1, 240, 1. That's what the look back means. So of course you can adjust based on your length. Since every single point is 10 minutes, this is 2,400 minutes, which is 60 hours and so on, so 5 days. So we want to predict the next 10 minutes in 5 days. Most likely it's not going to work very well, because you want to predict a short amount of data in a long amount of data. But let's see what happens later. Okay, so step, ignore this. We're not going to use a step. It's just a way that instead of using 240 at one shot, you can get a bigger one and then slice it down, so on. Delay, also ignore it. We're not going to be using it here, while the batch size is 64. So keep that in mind. I'm going to show you how it is done later and so on. So in this case, don't care about too much. What you need to understand is that what this step does is a flatten layer. So we're using a layer of 240. So we have 14 different variables over here. So we have 14 variables. So this is our look back, which is 240 units, because we're looking. So for predict 1, we predict the first data point, we take 240 of them, but this is only a single variable. So in this case, you have 240 times the number of variables. So for every point, you actually have 14 rows over here. Let me just do it again. So 2, 3, 4, 5, 6, 7, 8. Yeah, now it looks at poop now. 10, 11, 12. So this 14 times 240 array will be used to predict a single output. Okay, so that is why you need a flatten layer. So what does a flatten layer is that you do, instead of feeding it this array, which is 240 times 14 variable long, okay, to predict one parameter, we flatten it down to a neural input of 3,360. Okay, so we can actually just have a run of it. So we are training on number 1 to number 30,000 of that for our data, and we are using a 240 units look back. So this is going to take a while. So we're using ReLU because all data is run through a min-max normalization, so it will be between 0 and 1. So ReLU makes kind of a sense of it, so it doesn't go above 1, it doesn't go below 0, and we have 128 neurons, 64 neurons, and 1 neuron. So it's a 1 output, so 1 neurons, because the target will also be 1. So we're not going to go too much on the generator function. Let's see how much we can get for 3 epochs. So there are a little bit of trick on the losses you can see here. I hope that you're able to see, because it's kind of light over here. See if it's still recording. It is still recording. Very nice. So it's 0.2523 after our first epoch and 0.073 in our second epoch. So this is a really good output, because it actually decreases. If it doesn't decrease, then you're in a huge trouble, because when we set up a model over here, all the neuron weights and their biases are put in randomly. So what does the optimization do is that they're trying to adjust the weight and bias of individual neuron so that we get a better input to output generation, if that makes any sense to you. So we're trying to get a better data out of it. So we're not going to use too many epochs here. If you run yourself, make sure you run until it's stabilized. I'm going to show you how to do that later. Okay, so we can see the first epoch have a loss of 0.2523, 0.0761 the second one, and 0.0581, which is great. So they are able to do a certain losses. And when your loss curve looks like this, it is necessary to run more epochs and see what happens. But I did run more, it doesn't actually go down further, so it might be different from your case because of the random seed that we generated in. But you are not going to get much further with a simple flattened neural network like this. So now what we do is that we try to plot out our data on the index that we do not see. So we train our model on the first 1 to 330,000 data point, and then we're trying to predict on the next 20,000 data point, which is from 30,000 to 50,000 on the index. So we are trying to do 176,000 of them, because we have to minus the 240 look back that we're trying to do. So we are not going to look at the first 240 of them and only start after that. So that of course depends on your generator functions and how it works. It might work slightly differently, but the concept is that we are trying to plot the data in a data set that never seen before. So this will actually predict the data, and it will predict the data based on the model, and the last 3G plot will plot the original data point as blue and plot the predicted data point as red. So you can see it's kind of rubbish, which is what we expected. A flattened layer might perform very well on the data that you have seen, which is the training data, but you go to the prediction data, it just loses in mind. It doesn't understand what it wants, and you just output everything as, you know, a flat line, because they never seen data point before. They're confused. This is a bad model. We should not use that. Okay, so, which is, I think, the other thing about, it's not that easy to just, you know, fit it. Optimizing a model is a lot more harder than actually writing a model, because syntax are fairly straightforward in Keras, and if you are not able to produce a correct model, understanding a syntax is just the 20% of the work over here. Okay, so in this case, we are trying to go into our actual LSTM over here. But before we actually go LSTM, let's go a little bit into what is a bloody generator function. So we talk about a generator function above. It's actually a long function. Here you can actually have a look. So this is actually directly from the tutorial, and you can actually make any adjustment that you want to it if you need to. Okay, so what we do is that it's a custom generate function. Instead of feeding a generator function into the Keras, this is trying to produce a matrix. So let's just run this. It's going to take a while. So the problem is that due to the memory limitation and the time limitation and, you know, computation limitation, we do not want to wait that long for this to run. You can see this is only until 1005, so this is going to take a while. So I'm only running the first 1 to 10,000 of the data point, and only on the second column. So we are throwing away all our variable over here just to make this example happen. So in R, it's slightly difficult to understand what it means. Let's go for our Google Sheets over here. So let's say you have an original sequence of 1 to 68 over here. So it can be very long. So this is sequential data. You can see every single data point is dependent on everything before it. So it's just addition data point. So in our LSTM, you should be able to predict, let's say, 10 from 1, 2, 3, 4, 5, 6, 7, 8, 9. So you should be able to predict 13 from 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you should be able to do this kind of time series prediction. So what do we do in a normal machine learning model is that we separate them into input and output. Very simple, isn't it? Very straightforward. So instead of using 240, which is too long for my Google Sheet, let's just do our loop back, which is our element for prediction, into 5. So let's simplify it down a little bit. So if you only have 5 elements and you want to predict the next one, this is roughly how your matrix should look like. So if you look at our iris data point, iris model that I do for a neural network is fairly similar. You have the sepal width, length, and you have the pedal leaf length. Sorry, not the other word that I just said. Well, I'm not going to get monetization from now, isn't it? Okay, so in this case, we're using 5 data points to predict the next one. So if you unroll this original sequence into what we need for machine learning prediction, it will be 1, 2, 3, 4, 5, followed by 6, which is the target. So target is I, this is I minus 1, minus 2, minus 3, minus 4, minus 5. So if our target is 17, our input should be 16, 15, 14, 13, 12, in that order. Okay, so essentially what we do here is to convert this 1 to 27 here into a matrix that can be fed directly into any machine learning model easily for the prediction. However, you can already see from 1 to 27 over here, it's just 27 elements. It becomes how many elements? So it becomes 132. So the equation for calculating how a matrix size is going to be, if you're doing this kind of passive or manual calculation, is if your input is 1,000 element long, your loopback is 5, let's say using the same example here, the final array is going to be 4,975 element big. So this data it's going to blow up really, really fast. Let's say we're doing 30,000 of them, and we are using 14 different variables. our loopback is 240. So our calculation will be, sorry for the keyboard noise over there, I'm using a mechanical keyboard, so don't kill me. So our final array, instead of just 30,000 times 14, which is this times this, for 420,000, not a crazy number. Our final array is going to be 422 minus 240, because we cannot predict the first 240, there's no input for that, times 240. So it's gonna be I can't even pronounce this word anymore. I don't know how to pronounce this word. So it's gonna be 100 million and so on. So this is gonna kill your RAM, because when you want to do a model fit in Keras, you have to fit the whole array there into your RAM. So it's gonna be really hard. So what does the generated function do is that we do by batch. So instead of fitting this whole bloody humongous object into our RAM, what we do is that we fetch them by batch. So if you say I want a batch size of 22, what essentially it does is to take the first 22 elements over here and fit it into the model, and we take the next. So once this is done, we take the next 22, we fit it into the function, we take the next 22, we fit it into a function, so on and so forth. So after I finish this, we should have already done our matrix. So I can't really show you how the matrix is going to look like. You can actually look at here. It is an array of 10,000 times 124 times 1. So it's going to be as big as this. I'm sure there's something wrong with it. I don't think there's anything wrong with it. Yeah, but you get the idea. I think it should have 240 less. I don't know where does the rest come from. So it might be using some future data for the prediction. I'm most likely going to use the future data for prediction. Let me check and get back to you on this one. A few moments later. Hello, I'm back. I figured out what's wrong. So the problem is that when we specify it to be 10,000 over here, where's my generator functions? Over here, no, not yet. Where's my generator functions? That's so confusing. Okay, so when you specify 10,000 over here, you actually just throw in 10,000 data. However, the last 240 would not actually be of any data, because you have to sacrifice the 240 element in the beginning for it to work. So if you actually run a tail, which actually shows you the last few elements of the data over here, you do find that if I do a tail on X for the last 1,000 element, you can see there's 240 NA data, and if you do run a tail on the Y on the last 250 elements, we do have 240 empty data. So there's no issue with that. So the equation and the function work as expected. It's just that I should not put 10,000 here, but it doesn't really affect anything. The network will ignore it in the end. It's just not very good, not very clean coding. Okay, so once we're done with that modeling, let me check first if the screen is still recording. It is still good. So let's just go for how do we fit the data into our model, and how would our model work. So instead of just a flatten layer just now, we are able to use an LSTM, because now we are feeding it an array. So the first 240 column is the input, and the last column as the output. So that's why our input shape is 240, which is our shape of our Y column, and the other, and it's a single dimension. So LSTM expect things to be in 3 dimensions. We only have 2, so we are going to put another 1 over here. So for the batch size, which is here, is 10,000. You do not need to specify. That is the batch size. We usually can just ignore, and the network will understand that I have to run it 10,000 times. So we are using quite a deep neural network over here. So there are 4 layers. Feel free to mess around with it and see what happens. So this is just what I use, and it's kind of give me a reasonable amount of performance, but not really well. End of the day, this is only a single layer of STM. So let's just train the data and see what happens. So what does the batch size 100 means is that every single time for that 10,000 line, you will fit in 100 lines. So instead of doing 1 by 1, which is going to take a long time, a batch size 100 will fit 100 data in directly for the computational and the prep propagation, and it will slightly speed up the process. So increasing that will speed up progress, but also result in maybe it would miss the local minimum and so on. So for epoch, it will depend on how much confidence do you have in the overall idea, and how many do you want to run it. Usually we run it until there's a stabilization in either a loss of the training set or the loss of the validation set. So in this case, we're using a validation split of 0.1, which means that 0.9%, no, 0.9 means 90% of data will be used for training, while 10% of data will be used for validation, which is why if you go down a little bit, sorry, this is a little bit light, I can't really show you how. Let's show here. So here you can see. So for the first 9,000 data, it will be used for training, but the last 1,000 sample will be used for the training. So the good thing about here, the loss is extremely low. We're going into 10 to the power of -5 for the losses. So I think 5 epoch should be more than enough for us, for the network to understand how does it work. And validation loss is NA most likely because of the 10,000 of the 240 empty data that we do in. And for your case, for your education purpose, feel free to remove it and see the validation data come back. So we are on our last epoch, as you can see, because this is a model fit itself, we do not need to compute the generation of array. So it's pretty fast and pretty straightforward compared to a generator function that we did previously with the other flatten layer that we did. Okay, so we are almost done with that. 3, 2, 1, that's where validation split and plot history. So you can see actually after the second epoch, the data doesn't significantly decrease anymore. So let's scroll down a little bit. You can see our validation data, there are the two similar plot to each other. It goes down the second epoch and stays roughly around 0 because there's not really much room for improvement when you're that near to 0. Okay, so once we're done, let's try to plot the data out. So in this case, we're using the 30,000 to 50,000 range of the data. Well, we're training on 1 to 30,000, and we're predicting on 30 to 50,000 to make sure that the data that we train on is never seen by the network before. So the batch size here is going to be 17,600, which is 20,000 minus the loopback. So in this case, I don't think you need to minus loopback because they will actually do some clever way of calculation in the generator function that I do not write. But just for the safe side and just to make sure that it runs well, I'm going to reduce it by 240. However, so no, this is not 240, it is 2004. Never mind, the concept remains. Let's just correct it right now. So 19760. So this reduced by 240. Let's run it again. As you can see just now, the data generator is pretty great for such a short training time and such a short training set. And I actually make some mistake for this computational. We do not train on the first 1 to 30,000. We only train from 1 to 10,000 using a single variable as an input instead of the 40. So it should give me now. So it works great actually. So if you are a machine learning scientist that do not want to explore further, this might be more than good enough for you what you need to do. The data looks great, the fitting looks great, and the training is quite fast and so on. However, if you do want to use all the parameter, we're going to run something slightly different down here. So we have changed a bunch of parameter over here. So the first is that we use a generator function. So what does a generator function do is that it will take loopback on 240 and fit it in batches of 128. So what does that mean is that it will fit in a size of 128 array like this to predict 128 of them at once. So that's every single steps. So if you go back, there's also other thing called step per epoch over here. So what a step per epoch means that they'll run 20 steps. So every steps you have, let's put the calculator over here, you have 240 on the loopback times the batch size, which is 128, times 20. So this should be, this is how much the data, every single epoch should be looking at. So it is twice as much our training data. So that will mean that every epoch you will look through our data twice. So if you are not confident, you think that that's too slow, of course you can split it into half. So you can actually half the step of epoch you have, you can half the batch size that you have, or so on and so forth. Then feel free to mess things around. So instead of the LSTM, we are also running a GRU, GRUs, the gated recurrent unit like this over here, and we try to see what happens, just to mess around the data and see how we can change things and how we can mess around with things and how does different model work. So the difference between this and what we did just now is that what we did here only use a single variable. So it might work great for this data set, but it might not work very well for the other data set, or it's not a good educational process if you just do the single thing and it works. Yeah, so I'm a little bit surprised because it doesn't work that well previously. But it works really great now because maybe because the random set is different and there are more training stuff that I use. So you can also see that I also changed the optimizer and the loss functions because realistically there are very different data set. Instead of dealing with a single input, now we're dealing with 14, and instead of using STM we're using GRU. So there are a lot of things that might change. I expect this to be rubbish because I simply changed them. No, actually I don't simply change them. I change them on purpose so that it will not perform as well. But then I can show you how it works later. So there are 5 epochs, so it's going to go through a lot of data points. So let's go through a little bit of what we did just now. So we have the data set, which is the data for the temperature from 2006, 2009, 2016. Every single 10 minutes you have all the parameters collected by the weather station. So the RNN is a tau neural network model that are sensitive towards time series data or recurrent data, where they are able to remember their previous state and makes prediction based on their previous states. While the first thing that we do is a flatten layer, so the result for this flatten layer is just kind of rubbish. They're not really any useful in predicting the data because they are not time sensitive. They just simply squash an array into a single element, single dimensional vector. So it's always not a great thing for that if you want to do a slightly more complicated data. So what we have done just now is to use a single layer LSTM, and this is actually not LSTM, this is GRU. So this is LSTM and fit into a normal neural network. It's kind of a shallow network. It's only 64 unit and 4 or 5 layers, but we're using a custom data unrolling. In this case, it means that we are not using a generator functions. So it's only fit in a single variable. However, in the next one, example 3 that we're trying to run here, try to include all of the variable that within the data set. So let's see if it actually do any difference, shall we? This is just water. I'm just using a bottle, so don't worry. My mind is very clear. Okay, so as you can see from the loss over here, our first step actually yields 0.0996. Which is great because in the second step it got reduced by half. So as I said earlier, if your thing doesn't decrease anymore, means it kind of have reached a local minimum or global minimum. So any further training might not be very useful, and if you train until the loss is super low, you might actually be overfitting your data to your training, and it might not perform very well on your validation and your training and predicting set. So it might not work well on the rest of the data over here. So we have one more epoch. This is going to take a while because GRU and LSTM itself is kind of hard on the computing to calculate compared to the fit for network that we did just over here. So you are using just a model fit, and you only use, sorry about this one. So if you only use like a flatten layer here, where we do not have any LSTM layer or GRU layer, it is much more computationally efficient because the number of things that it has to calculate is small. So it's a lot of unit, but it's faster to calculate, unlike LSTM, even though they do not have a large number of things to calculate. Like here, they only have 22,000, but as you can see, the time is a lot longer. It's 24 seconds. If we go up, it's, how long is it? It's 25 seconds, so it's about the same. Well, not a very great example because we're using 24 versus 1 parameter, but you get the point. Now, LSTM itself is not as efficient as a normal neural network, and it is going to use a lot more time to train your data. Well, I should be better prepared for when I do my video, isn't it? So we have another few epochs. Let's see what we can do. So in the meantime, let's talk a little bit more about our predicting function. So our best side plot is how long you want your x-axis to be, while the loop back plot should be exactly the same as what you trained just now, just to make sure that the model understands how to work. And you change the parameter you're predicting, usually you result in an error. while a predictor function over here use data as the input, look back as this look back plot, which is 240, delay, you can ignore it, we're not using it over here, and we are plotting it from 330,000 to 50,000, which is the data point that our training network have never seen before. So shuffle is actually, do you want to shuffle the order of the data? So in this case, we do not want to shuffle the order of the data, otherwise we can't actually see how it performed in a series, and it will actually mess up the data a lot. So step you can kind of ignore, while the batch size actually you can also kind of ignore, because for a batch size not relevant to the prediction and so on. So what we do is that we actually predict data. We have a predict generator, which is this function, and what a predict generator does is that actually it will generate a prediction generated data. So if you actually see here, which we done earlier, so predict generator has it's a list of two elements. The first list has the target, the first list has the input, which is in this case, in our last example, 19,000 lines times 240 times 40 parameters, while this one has the target. So every single array over here will be directly correlate with one element. Okay, so I think our training is done. So let's run our predicting function. So once of course you get the predicted data, you can actually okay, so once you get the predict data, you can actually feed your predicted data, which is this, and use this as an input. Remember, the predict generated data set is the data set you use for prediction. It's not the output of the prediction. Yeah, that's kind of confusing when I name it that way. So what you do is that this will be the target. So the second list will be the target they want to achieve, while this will be your input. So what does the chunk actually do is to take this data, predict another list based on the list 1, and that will actually give you all the answers, and you compare the answers to your list 2, if that makes any sense, because everything here is taken the raw data, which is the original data. So you take this out, you take the input data for prediction, feed it into a normal, get the predicted output, and compare your predicted output to list 2 over here, which is your target. I hope that clears things up a little bit. So you can see it's kind of rubbish, because it could be the GRU layer is rubbish, it could be the LSTM layer is rubbish, it could be a lot of things that is rubbish. But that's why we need to do, that's why there's a lot of optimization needed before you actually run a model like this. So let's say we're not running GRU, we want to run LSTM, and we'll see what happens over here. So I might want to skip forward so that you don't have to look at me for 10 minutes here doing nothing. So should I actually record this, or maybe I should stop and come back, just so that I don't waste my memory on a much longer video than I need to. Yeah, I'll come back later. A few moments later. Hello, I'm back. So we are running the LSTM layer just now. So the training actually doesn't end very well. It doesn't actually drop too much below the initial epoch. So let's just plot the data and see what happens, shall we? So I don't expect things to run very well just by changing GRU and LSTM without tweaking a lot of parameter in between. So what we can already know from the beginning of how our custom function works so well and our generator function works so rubbish is that by only feeding a single parameter into our data set, it might be a lot, actually, yeah, LSTM actually perform a little bit better than GRU just now, but continue from what I said just now, using a single parameter for the prediction might actually be better than using all the parameters, because they might not be relevant to the data set at all. So let's go to our final data point, which is data reduction, data remodeling, and some neural network model optimization that we need to do before we can actually get a working model out. So that's what we done just now. Single layer GRU LSTM into neural network using generator function doesn't really yield a very favorable result is not complete rubbish, but it's not very useful if you want to predict the next one and you see the loss between all this thing is so high, so on. So what the first thing we need to understand is that how do we select data for the neural network. So it's very important that you select data that cover a wide range of things, and you don't select data that only say between 1 to 5, while the other part of your network has 10 to 25. So the training data needs to cover the range of the prediction that you want to do. I think that might be one of the reasons that we failed just now. So I don't know how to get this to actually do the metering correctly. Yeah, hopefully it's okay. So in this case, we are actually scaling down the raw data. So just now we feed all our raw data, which is 420,000 line over here, and we limit the data only to 50,000 to 100,000 over here. So we scale down the data so that when we do a mean and normal scaling and normalization of data, our 1 will actually be a maximum, our 0 will actually be a minimum. So when we do all this thing, make sure the data is in the correct space. So let's run this. So this should actually give us a lot of plot. So I do this plot, which plots the whole data only on our target, only our column 2, which is the temperature. So you can actually see we have minus 0.4 to 0.4, which is intended because I forgot to tell you this. Once we apply data normalization, which actually normalize data to between 0 and 1, I minus the data by 0.5. So that will shift the 0 to 1 down to negative 0.5 to positive 0.5. So that has two effects. The first effect is that we do not want to get too close to the edge of a activation function, because that kind of crush everything into the same value. And having a negative value will work better for our activation function later. So we're going to change it from ReLU to something else. Okay, so that will actually give us a good overview of data. We cover mostly from negative 0.5 to positive 0.5, with mostly things in the middle. So our training data will cover almost the whole range, and our predicting data is going to be within the range of our training data. So the prediction should work a lot better. So the second thing we need to do is that we need to determine what are the columns that are completely useless and we're going to throw it away. So if we actually go up all the way here, we see the raw data. We have the millibar, which is the pressure, the ambient pressure of the location. We also have T-spot, which is TDU, VLAC vector, SH, SOC, R row, max wave, and so on, things that I don't really understand how it's going to actually affect the temperature. If you do, you might want to do a data transformation, because let me show you how they look like. So I run a for loop to plot all the different data set from 10 to 20,000, which is in the middle of our data set here. So 10 to 20,000 right in the middle here. So and we plot in from different columns. So the first one is the first column. This is the second column, which is our target that we want to predict on, third column, fourth column, and so on. So by looking at this curve, you can actually see 2 and 3, column 2 and 3 are kind of alright, but you see column 14 over here. So if you are confused about 14, it's because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4. There's 14 different columns for 14 different graphs. So if you look at column 14, 13, and 12, I don't really see how this can be relevant directly without doing a lot of data transformation. You might want to do a Fourier transform, you might want to do a certain functions, apply a certain mathematics so that this data is able to fit the things that we are doing over here. I'm not sure why this pop up, let's close that. Okay, but directly looking at the data, you can see that the temperature to column 2 and 3 might be the most relevant in the prediction, and we can just throw away the rest and see what happens. So let's see, our data is actually the temperature for the temperature and the teapot. So this is in Kelvin, so it might be exactly the difference between things like that. So I don't know, you have to look at the original data, and it's encouraging for you to do that, because in environmental data is not really my turf and so on. Okay, so let's just regenerate a new object with only column 2 and 3, which is what this row is supposed to accomplish. So data 3 will only contain 2 columns. If you look at here, it only contains two columns, which is t degree and t pod k. So these are scaled, normalized, so everything is between 0.5 to positive 0.5, and now we're gonna fit into our neural network. So the first thing that I really changed is the look back. So we do not want to look at 2 days before to predict the next 10 minutes. If your goal is to predict the next 10 minutes, I only want to look back at 15, which is 15 times 10 is about 2.5 hours of data to predict the next 10 minutes. So that sounds more like a realistic plan of it. So I also reduced the batch size so that my training can be faster. You should be able to reach a local minimum faster, because now I have a lot less variable to look at. It should be a lot easier for the model to find how the algorithm for that to work. Okay, so we have seen the train generator before, same applies, but I added something called the validation generator. So what is a validation generator is that instead of taking data between 1 to 30,000, we take data between 30 to 40,000, which is the data that the training data will not see, and we validate our model on that. Okay, so the things also is going to be slightly different. Our network is going to be significantly more complicated than the single layer LSTM or GRU that we did just now. So the first layer is a GRU layer, which is the same thing. It has 64 units and it has an input shade of this, which is standard. I added this thing called a return sequence because we want the output of our GRU layer to be similar to fit into a next layer. So a next layer is actually a bi-directional GRU layer. So what the difference between bi-directional and a single directional RNN layer is that instead of just predicting one way, the layer will actually go two sides and try to predict the next one from the two sides. So it will be very important for certain things like a language where Mrs. Tan something something, and Tan will be related to by the thing in the back and not just in the front. So good morning someone, and that will also be influenced by the back. They are not a very good example, but you get what I mean. Instead of predicting things one way, you go the other way. So a lion dance and lions eat meat, and lion dance meat might be wrong, and lions eat meat might be a lot more relevant if you look at it. So lion and meat, in the middle, it might be lions eat meat, not lions dance meat, because lion dance and lions eat are perfectly legit example, but because of something in the end, we are able to better predict things in the middle. So that is what a bi-directional layer does. Okay, so everything in the back is similar. However, I've changed the activation. Instead of a ReLU, I've changed it to hypertangent. So you can look at this curve. A hypertangent has a coverage of negative to positive 1. So they are able to better work on the data, which I have already modified just now, which is between 0.4 to positive 0.4. Sorry, negative 0.5 to positive 0.5, rather than a ReLU, we just take everything above 0 and just throw it away. So I do not also want the data to be too close to the end, otherwise they get squashed into the... So everything close to 1 will get squashed into 1. This is how activation function works. So feel free, run around and see what you can do. So I've tried many different optimizer and loss, and I'm using mean absolute error. Feel free to change it to something else like the mean square error and see what you can do with it. Okay, so I know something also called callbacks. So callbacks is a way of preserving a current model, and by looking at a certain parameter within the training. So let me just run this first so that we can actually talk about it. It's easier. So in this case, a summary model, actually this one will actually give you a summary before the training. So a summary model will give you things like this. This is the 13 sequential model we have in this specific example, and we have the first GRU layer, which has 12,000 parameters. We have a second GRU layer. You can see it's 64 unit over here, but it shows at 128 because it's a bi-directional layer, so it has double the number of neurons within it, which is why our parameters to train go significantly higher, and it's going to be significantly longer to train this data set and so on. So we again have 64 normal dense neural network, which is just a normal neural network can connect one layer to another, and then 32, and finally we goes down to 1. So the total number of parameters to train is 70,769. However, it's gonna take a while because of that. Okay, so you can see the training is already stopped. So what's happening here is a lot faster than what we did just now with our single layer LSTM. Okay, so what happened here is that I use a much smaller number step per epoch. So it's very fast to train 35 of them, and I'm supposed to do 20 epoch of them, but I'm running and optimizing my layer based on validation loss, and you can see validation loss doesn't decrease anymore. So if you train your network so well optimized for your training data, it might not generalize to data outside of your original plot. So if you are training on 1 to 30,000 and you validate on 30 to 40,000, the data might not work at all on data it doesn't see if it's super optimized for training data. So we do not want to overfeed our data. I think that's technical term over here. So that I usually just pin our callback on validation loss, so that if the validation loss is higher, we stop the training and we only take the best model over here. So we restore best weight, so it will actually be the training weight of our second model. So on the training data, it might not work as well as the other one, but for validation data, this will work better, and so on. Okay, so now it's the same thing. We're trying to plot the data out. Remember, blue data again is the original data, while the red colored data is the prediction we take from the original. So you can see, compared to the LSTM layer, this doesn't perform well compared to our single parameters unrolling of the temperature thingy. But for custom generator function, you can see in certain part of it can fit extremely well. It's just that when the training data is much higher than the original one, it doesn't work that well. It could be because they are trying to prevent the over generalization, overfitting, but overall it is a lot better than this thing, and we are using a lot more number of parameters, and we're using a much more network size. It is not the best model. I'm sure that a lot of things can be done to make this better, but for an overall idea of LSTM, I do hope that you understand what it is. Just to make sure you do, let's go again on what we are trying to do with this data set. Okay. So first of all, what is our data set? So our data set is a model data collect from Amazon AWS, which is a temperature weather station data every 10 minutes for the last 7 years and so on, which is why you have a 420,000 rows of data with 14 parameters each at each data point. Okay, so this is, we wanted to use an RNN on this data set because it's a time series data when the next data point will be determined by the previous data point, and we can actually predict that based on what it is previously, which is why RNN is useful. So if we use a flattened layer, you can see that our result is actually kind of rubbish. So if we just feed in our result as where is our data point? I think this is the one. This is our flattened layer point. So this is our data. It is our model prediction if we only use a flattened data point. So it doesn't actually understand the meaning of one time point to another. It just flatten the whole thing, feed the neural network, and see what happens. So the training loss is not incredibly high. It's only 0.0581. However, when it goes to the training data, it never seen data before. It just give up and don't know what it should do. So what we can do about this is that we can actually try to emulate the idea of using a single layer LSTM using custom data unrolling. So the main purpose of me introducing this idea is that you have to understand how a neural network function generator works. So based on that, you can actually look at the RNN generator function breakdown. I'll link this file into the video description below so you can have a look at that. So in this case, if you are trying to predict 6, which is the 6th element in the original sequence, you can actually take the 5 previous point and put it in a data model, a data structure like this, where the first 5 columns is used to predict in 6 columns. So this is very, very standard in a lot of machine learning purposes. And if you're using Python, this 5 will get piped into one list, and this target will fit into another list. So a batch number is how many sequences that you want to fetch to it at once. However, if you don't use a generator function and you try to do the matrix manually, let's say you want to generate this matrix first before you start the training, it's gonna take a lot of RAM, a lot of storage, and a lot of time for you to generate. And in a lot of time, you might not need to actually fully generate your whole data set before you start the training and so on. So, however, the good thing is that we get an extremely low training loss, and we get an extremely well result just based on this custom unrolling, which tell us that there's a lot of rubbish in the data we might need to remove. So that is actually evidence in our next point, which is trying to use a single layer GRU and LSTM. I show both, and using a generator function. So by using a generator function, we are able to, of course, feed all 14 parameters in very happily, feed everything in and see what happens. However, because of that, I think there's too many rubbish in. The network didn't understand which one is more important than the other, so it just I don't know what to do. So it kind of create another flat line after you have done the prediction. So it's doing well among the training data itself. You get a 0.0487 of loss. I think this is a mean absolute loss. Yeah, so we get a 0.0487, but when it goes outside of the training data into the prediction data, it just completely give up and don't understand what it is. It doesn't even follow the trend of the original data set, because there are other parameters that are distracting the model from understanding what is the goal output that they want, because they are given too many data, they don't know which one is important and which one is not important. Okay, which is why here we're trying to do a data reduction. So one of the suspicious is that the data that we feed in is too different from data that we want to predict. So the model is not able to cover the overall length of the idea, which is why it's kind of failed, which is why I want to reduce the data down into only 50 to 100,000, which makes our scaling and normalization works a little bit better compared to the previous situation. And we also want to narrow down the columns that actually would make a significant contribution towards the prediction of our final data. So we only fit 2 columns into a model instead of 14. So everything else we throw away. So we also massively increase the network size by using a bi-directional GRU layer, and this result in a very good training data and training loss. However, because we're training data based on a validation loss, it stopped kind of prematurely in the situation, and you might be able to train it more and see if you can actually get a better data point. You might be able to use different data manipulation methods so that you'll be able to see if your result is better. So one of the suspicion that I have is that the validation data might not be enough. You might want to go from, let's say, 30 to 50,000. You might want to go from 20 to 40,000, so that it's partially trained and partially not. So you can mess around with it, or you can also increase the patience. So what does patience means is that how many steps of epoch you allow it to run before it actually stops. So in this case, they are able to, let's say this one is higher, don't stop it yet, wait for another one. So it wait for another one, it's still higher, nope, stop the training, is enough, and so on. So finally we plot the data. You can see that even though it doesn't fit extremely well to the model that we have, it doesn't have a super close model fitting as we did for the custom unrolling single layer LSTM just now. It might be more favorable because it is able to predict the trend. So when the original target goes up, it goes up. When the original target goes down, it goes down. So in certain region of the data is performed really well, but in certain region of data is unable to catch up. So it might be because our input data doesn't have enough training data for it to reach here. Well, because so it might not train enough on that region of data. So we might want to tweak our input here so that it's able. So what I meant is that it's only seeing maybe this part of the data and doesn't go all the way to the back. And yeah, so it might only train on the first 20,000 of data. It doesn't go too much in the back in the training process because it's kind of stopped prematurely, and you might be able to increase the result with a different, let's say, batch size. So if you batch size to 100, you should be able to get a better result. I'm not going to run it. I think you should run it, and if it actually works, I would like to know. I'm going to run it, but I would like you to comment down below if that works on your case. So you can find, again, all the scripts and materials that you need, as well as the original reference material that I refer to in the video description below. Thanks you for watching. This is extremely long video, so I hope you like it. Subscribe, like, bye. I don't know how to do this thing. Bye.